Now, what's special in this case is not only we have the value of u in the minimization statement, we also have the derivative of u. So what is the derivative of u within these three elements? Well, we can just look at the formula, right? Du dx in the first element, what is it? It's a linear function always, so it's 3u1, right? Okay, and my du dx in the second element, what is it?
Three times the quantity u2 minus u1.
Yes, 3 times u2 minus u1. And I think I've made a mistake in the third element because I don't actually have u3, right? u3 is equal to 0, so we have actually 0 here. All right, so my derivative in the third element is actually what? Minus 3 times u2, right? Okay, so this is what we have as the derivative and the function. Now let's plug it into the minimization problem. We are minimizing, again, we want to split this integral into the summation of the three elements. So the first element, integration from 0 to a third. Let's actually write it in different colors. 0 to a third. We have rho g times u, which is u1 times 3x, okay, plus my t times 3u1 squared, so 9 times u1 squared dx, okay. And our second element is integration from 1/3 to 2/3. We have rho g. Now we have this looking like a complex function here, u2 minus u1 times 3x minus 1 plus u1. Let's put a parenthesis over here, plus t times 9 of u2 minus u1 squared. Okay, that's multiplied by dx. That's our second element. And we have our third element here, 2/3 to 1. Again, we have rho g, and my x here is going to be minus u2 times 3x minus 2 plus u2, okay, and the plus t times 9 times, well, 9 times u2 squared dx. So this is the final minimization problem here. And now it's actually should be pretty clear, right? So this is a quadratic function of u1 and u2. For example, all the square term over here actually doesn't involve x at all. So they basically pull directly out of the integrals. And you just need to multiply this constant with the length of the integral, which is 1/3 in every case. So basically, the 9 becomes 3 when you pull out of the integral. And the linear terms you actually have to integrate, and you're going to find out what the integral is. You can either do it analytically, as actually it's easy in this case, or you can do it numerically, and that's something we're going to discuss in our next lecture. Is there a way to programmatically evaluate these integrals, which are going to be coefficients on top of the linear and quadratic terms when we perform such optimization problems, right? So basically, we want to figure out, is there a way to not having to do all these tedious mathematical derivations to figure out what is the formula of this optimization problem, so that we can apply the same idea of finite elements, but without having to go through all these derivations, all right?